All right, thanks for sticking with us, guys. I'm Erik Taubeneck. Hi, everybody. I'm a software engineer at Game Changer. We've got like stickers all around, and if you guys we're here for the last talk and are into Docker, you should check out my coworker Travis Thieman's talk tomorrow. He's talking about how we use Docker to do all our local development stuff. It's gonna be a cool talk. But now we're gonna go on to do some math. So just a real quick outline of what I'm going to go over today. We're going to do a real quick crash course of some calculus, sort of remind you what the derivative of a function is. This is the mathematical derivative, not sort of financial derivatives or any of that nonsense. We're going to talk about the finite difference method, which is a common way to estimate the derivative using a computer. That's going to raise some issues, and so to dig into those issues, we're going to talk a bit about floating point arithmetic and some of the nuances there. And then we're going to get into some complex analysis. We're going to use some imaginary numbers, which is always very fun. And then finally, once we've sort of gone over that and refreshed you or maybe taught you, we're going to use that to hack the derivative and do a lot better than finite differencing. So I encourage you to play along if you so wish. I have thrown a package up on PyPy called Hack the Derivative, and all the functions that I use are in there, so you can like try it out yourself if you so wish. It's just pip install hack the derivative. All right, so a little crash course. So we're going to consider some function f. And it's going to be a real valued function that maps from R into some subset of R, or maybe the full thing. So a few functions, for example, are x squared. That's going to go from every real number to all the positive real numbers. Sine of x, which can go from every real number to real numbers between -1 and 1. Or this final function here, which is going to go from every real number except 0 to some other real number. I think that covers everything. So yeah, so these are just real valued functions. Cool. So the derivative of a function is essentially the slope of the tangent line which intersects the function at a given point. So the derivative is just a function that tells us the slope at every point. So we have sort of a graphic here where we have some function that's curved, and then we have a straight line that is intercepting it at one point, x, and the slope of that straight line tells us the derivative of that function. So this is a little wishy-washy and geometrical. So formally, in math terms, the derivative is defined as the limit of f of x plus h minus f of x over h. And that derivative needs to exist from both directions. So coming at it from at 0 from negative numbers and from positive numbers. And so essentially what we're doing here is taking like a very small step and then computing like rise over run of that line. And then if that thing gets closer and closer to a number, then that's the derivative, and the derivative will be defined. So we can work through an example of this. Let's take x squared. So now we can plug this in. So we get x plus h squared minus x squared, and we can do our FOIL and whatever, and some things start to cancel out. We can cancel out an h, and now this is really easy. As h goes to 0, that's going to be 2x. Probably most people who've taken a calculus course can have seen this and know how that works. So now suppose we wish to find the derivative of f of x at some given point. So one approximation that's commonly used numerically is finite difference. And all this is we take this derivative and we say that it's approximately equal to this function for like a very small h. Now we can't let h equal 0 because we can't divide by 0. So we just like take some small value and take a very small step and say that's probably pretty close. So this is pretty easy to implement in Python. Just looks like this. We have to give it an h and whatnot. And so we can define our x squared function and plug in and say what's the derivative at 1. And when we put in some really small value and we get we get some zeros, it looks pretty good. So now ultimately becomes a question like, how do we choose that h? Like, can we just put in 1 with a few zeros in front of it? We really want like a really small h because the limit is as it approaches, so it's going to get better as it gets closer to 0. So maybe we could take like the smallest number that we can represent in the computer. And so in Python, you can get this by going to sys and float info and finding the min float that we have. So this doesn't work. This 4 zeros and a 1 behind the decimal seemed to work pretty well earlier. Maybe that'll work. Well, if we take a really big number, say we want to find the derivative at 1 with 20 zeros, I don't even know, a gazillion or whatever that is, and plug this in, that doesn't work either. We get 0 too. So that's breaking. To understand sort of why that's happening, we need to sort of dig in and understand the floating point numbers a little bit better. So we're going to deal with 64-bit floats. This works equally well with 32-bit floats. The representation is slightly different, but essentially the way this works is you have a floating point that's broken up into 3 parts. The first part is the sign, so it's just whether it's positive or negative, and that just needs 1 bit to tell you that. You get 11 bits for the exponent, and so this is 2 to some power, so we get 2 to an 11-bit number, and that goes from negative 1023 to positive 1024. And then we get 52 bits. That's a fraction. That is basically our the amount of decimals that we have to represent the number. So that's like how accurate it can be. So that's represented in, if you like binary form, the top one. If you like sort of math summations in the bottom one. We don't really don't worry about trying to understand this too much. It's analogous to thinking of like a 10-digit number in base 10, scientific notation that you're probably a little bit more comfortable with, like this. And so multiplication and actually division, since division is just another type of multiplication, get huge help by associativity and commutativity. So this is, we can just get rid of those parens, and then we can rearrange things, and then we can add those parens back in. And both of these are very easy operations that the computer can do. You don't lose any accuracy on the left, and on the right, you're just sort of adding the 2 things. And so you still, get your 10 digits of accuracy or whatever it can, converts to in base 10, and your exponent can just work out. If you're trying to do addition or subtraction, which is just another type of addition, this doesn't work. You can't rearrange these. And so in this case, like when you try and add this number on the right and you only have 10 digits of accuracy, you're not going to go anywhere. This is just going to be, the number on the right might as well just be 0. And so this means that the floating point numbers and the way that they're implemented, there are gaps between them. Sorry, that graphic didn't turn out as well projected as it does on the computer screen. But the idea is that there are gaps between each number. So for any given floating point number, there is a next floating point number. And the gaps between those at some places in the floating point numbers are actually bigger than other floating point numbers themselves. And so that's how we get this thing where we can add 2 floating point numbers and not actually go anywhere. And so to deal with that, we can actually write this function, which is like a plus epsilon identity. So we can take, some number and then some epsilon and say, if we add those 2, do we go anywhere or do we just like stay at the same place? And so at 0, and we use our like min floating point number, we actually do go somewhere. But as soon as we get up to like 1, we don't go anywhere. And just like we saw, if we go up to this big giant number and even add like 1 to it, we don't go anywhere. So this is pretty important if we're trying to take small steps to estimate the derivative. So if we choose an h that's too small, such that when we add the 2 together, we don't go anywhere, well, then when we look at this equation, we really, like f of x minus f of x is just 0, and we get 0, and that's not very informative. That's missing the point. This can obviously also happen when, even if we maybe step somewhere with x, if we apply the function and then can't go anywhere, we'll have the same problem. So how do we choose our epsilon? Essentially, we want sort of the smallest number that we can get to around the value of x. And so this is a function that basically steps around and tries to, like, starts with a fairly large number and then keeps dividing it until you add to it and don't go anywhere, and then it gives you the last one. So it's the smallest number which will take you somewhere at wherever you are in the number line. And so for at 1, this is like 2.2 to the negative 16. At 1 with 10 zeros behind it, it's 1 with negative, or 1.1 to the negative 6. And at this really big number, it's actually like 11,000. So the gap is like really big out there. I found these like lecture notes online that seemed to that gave this like pretty cool Taylor series, and it seemed pretty legit. I didn't actually work it all out, but I think it's pretty good. And they basically say like, well, you normally don't actually know this thing, so this is sort of the best estimate. So if you you take the square root of the sort of base epsilon at 1, and then times that by either the absolute value of the x or 1, so you sort of always get to 1. This is generally sort of what you should do. So we can redefine our function and say if we don't give it an h, like a custom h, let's just use this thing. And so we can test that out. So we can actually define like an error and an error rate function, which basically we're going to say we have a function and we know the derivative, so we're going to give it to both of these and then say like how far off is our estimation from actually computing it. And so we can use our example where we know, the derivative of x squared is 2x. And so using this, we get a pretty small error rate. These are pretty good, like 9 or 8 zeros, and then, that's pretty good. Even way out at that big number, this works pretty well. So let's try it out with sine and cosine. If you remember, cosine is the derivative of sine. So that works pretty well there. Oh, not so well there, and not so well out there. So we can do better. But we're going to have to use some math. So we're going to talk about some imaginary numbers, some complex numbers. Has anybody in here not seen this equation before? Anybody not seen imaginary unit? Okay, cool. So why do we need this thing? Well, if we want to solve the equation x squared plus 1 equals 0, we need some value that is, when squared, is going to equal negative 1. If any real valued number that you put in there, when you square it, is going to be positive. When you add 1 to it, it's automatically going to be greater than 0. So we need like these new numbers. So we create the complex numbers. And those are basically just defined as x plus iy for every x and y in a regular r squared grid. So a fun fact about the complex numbers: every polynomial of degree n gets all n zeros in the complex numbers, which doesn't happen in the real numbers. All right, so another example. So we have z squared. Z is just going to be equal to x plus iy, and so we can plug that in and we can square it and we can FOIL it out. And this ends up becoming the same function, just in a different form. Given any complex function, we can always write something in its real and imaginary parts. And so these are written as u of xy and v of xy. And so u is all the real stuff, and v is all the stuff that you can like pull an eye out of. So v is called the imaginary part. So in our example, x squared minus y squared is the real part, and 2xy is the imaginary part. And so these are both real valued functions. So now we have these two functions. There's actually 4 derivatives for a complex function. So we can take the derivative of u with respect to x, and we get 2x. The derivative of v with respect to x, and we get 2y. derivative of u with respect to y, we get 2y, and the derivative of v with respect to y, we get 2x. And so there's an interesting pattern there. Du dx equals dv dy, and du dy equals negative dv dx. And this is super important. In fact, this is the Cauchy-Riemann equations. And so for every analytic function, these equations hold. And so this is like a really awesome thing about complex analysis. If you've ever taken the course, like this is like the thing about complex analysis. If you want to see a proof of that, I just encourage you to go find your favorite complex analysis book and work through it. We unfortunately don't have time to work through that here. All right, who's ready to hack the derivative? All right, so we have some function f of z. Note that we're going back to our original function, which if it's a real number, the output needs to be real. And so we have f of z. We can rewrite that as u of xy plus I of v of xy. And now for every sort of z bar, the subset of z's which are real, we know that the y part is 0. So we can just rewrite this and plug zeros in for y. And since that function, if it's taking in a real number, it's going to give out a real number, we know that the v part is 0. So we basically have this function where f of x0 is u of x0. And so we want to estimate the derivative of df dx. And so that is equal to du dx because we have this thing here, which is actually also equal to dv dy because of Cauchy-Riemann. And so we go back and we can plug this in. We can use the definition of the derivative. And so we get this thing with the v's. And then we know that y is 0, so we can plug in our 0. And then the v part of x0 is 0. And so we just we get to get rid of the subtraction. This is the magic. Remember, subtraction and addition are terrible for floating point numbers. Division, great for floating point numbers. So now, if we want to estimate the derivative of df dx, we get, which is equal to dv dy, for a very small x, we just take the imaginary part of the function at x plus ih and divide by h. And now, since we're taking this derivative sort of in this other direction, we can just take a very small step. We can take the minimum step and we just multiply that by, so in Python, the imaginary unit is called j because i's used for counting things, so they just took j. It's also, for some reason in physics, they like to use j. So don't get too confused there. J is the imaginary unit. And so we're taking that function, we're taking a small step in the imaginary direction, and then taking the imaginary part of that and dividing by h. So now we've got that implemented. Let's try it on our functions. Boom! Exactly correct. Boom! Exactly correct. Exactly correct. This is awesome. The first time I saw this, I was like, what is going on? And so, you know, obviously we know it's exactly correct. The error rate's 0, the error rate's 0. So let's try it with sine and cosine. Note that we need the complex versions of sine and cosine because we need to be able to compute it at this complex value. At 1, it's exactly 0. Oh, wow, everywhere it's exactly 0. It just works. All right, well, maybe not everywhere, but that's still way better than we were getting for finite differencing. So let's take something a little bit more complicated. I looked this one up online of like favorite hard derivative problems for calculus students. And so this was the problem and the solution. 0, all right, just a little bit more than 0, a little bit more than 0. I mean, this is like way better than we were getting for them from finite differencing. And if we go a little too big, we get an overflow error. So it doesn't work everywhere. It has some limits, but it's still pretty awesome. So there are some limits. Like we saw, we need to be able to implement the complex version of the function, and that may not like work everywhere. It's also not going to, the Cauchy-Riemann equations aren't going to hold for non-analytic functions. So like absolute value is not going to work. Absolute value like doesn't have a derivative at 0. A function with like a less than or greater than, complex numbers aren't ordered. You can't say if one complex number is greater than or less than another one. So that's not going to work. There are some workarounds, but it essentially breaks your functions for everything else. So it has to be a very specific application that you're going to use those. And it only works for functions that are from R to R. So if you have some function like e to the I pi x, or z rather, like that thing's not going to work because that's going to take real values into complex values. Cool. So that's all I got. This is, if you want to check out, like I've got the slides up already, and you can check out other presentations I've done there. You can check me out on Twitter and GitHub. Yeah, thanks.